Let's take a look at one more example with exercise 7. An atom is inside a sphere and is equally likely to be anywhere within the sphere. So we've got some sort of atoms bouncing around inside here. What is the probability that it lands closer to the center of the sphere than the outside of the sphere? Okay, so realize that when we're looking at the atom and the position of the atom, it can be, even though it's inside of a sphere within some sort of contained region, there's still an infinite number of places where that atom can possibly be, which is kind of hard to count. It would take you a little while. So instead, what we're going to do is we're just going to compare some volumes. Now, some people would look at this and go, I don't have to do any math. It's obviously just going to be a half. Let's say I take a sphere and put it on the inside of this thing. That's half as big, or I should say the radius is half as big. Where'd you go? Okay, the radius is half as big. Because if I'm inside that inner sphere, anywhere inside that inner sphere, it's got to be closer to the center than the outside. And so the probability is a half. But is that correct? Well, here, let's back this up a little bit and let's start thinking of geometric probability in terms of lengths and areas. So let me back it up just a little bit. Let's do a similar question on a line segment. Very similar question on a line segment. You know what? This should be blue to match the sphere, I'm thinking. Ooh, this is kind of a purpley blue. Ooh, that's real nice. All right, let's say that this segment length is 1. It's 1 meter, 1 inch, whatever it is. Okay. And then we're choosing a point at random, and we want that point to be closer to the center or the midpoint of this segment than it is to the two endpoints, which I'll just conveniently call A and B. Okay. Well, does it make sense that what I need to be is I need to be within half of the distance between A and this midpoint here, or half of the distance in between, let's say, our midpoint and B. So basically what I just did is I broke that up into 1/4, right? That this is a fourth, a fourth, a fourth, and a fourth. So if I measure the part that I want as far as successes go, it's a fourth plus a fourth is a half. So if my probability of K closer to center, that would be equal to what I want, the length that I want is a half over everything that's possible is 1, which is a half. Okay, so you can see that whenever it's talking about lengths, one dimension, then a half does make sense to be closer to the center. Okay, but here, let's talk about something that's two-dimensional. Let's do it with, say, a circle. What happened to the bottom of that circle? Got all wrinkly. Okay, so same kind of situation. Let's say that I want to pick a point, or I have a randomly selected point, and I want to know what's the probability that it's going to land closer to the center than it is to the outside. So once again, I am going to draw a circle on the inside of this. Read. Okay, there we go. And I'm going to say that its radius is going to be half as big as what we started with. To make this real easy, I'm going to say that the inner radius here is 1, and then the outer radius going from here all the way to there, we'll say that's 2. Okay? So I'll repeat that same exact kind of geometric probability problem here where K, I'm picking a point K, and that it's closer to the center of the circle. Okay, so closer to the center of the circle is going to be anywhere within this inner circle that's right in there. What's its area? So I have to choose area because it's a two-dimensional figure and the point can be anywhere within that circle. So the probability on top should be pi times 1 squared. All right, and then where can it be chosen in total is anywhere within the whole entire big circle, which has a radius of 2. So pi times 2 squared. And then whenever I simplify, I get pi on the top and then 4 pi on the bottom. Do some cancellation with some pi's, and I get, whoa, back that up. Keep it consistent, please. Delete you from YouTube. All right, so this time you can see that the probability is a fourth, right? When we're dealing with a two-dimensional figure, to be closer to that center is going to be a fourth instead of a half. So I wonder then, let's try to make a conjecture. What do you think? It looks like it's not going to be a half, because that worked with one-dimensional things. Two-dimensional was a fourth. What do you think is next? What do you think is next? So here, let's repeat this process now with a sphere on the inside of this thing. Okay, let's put it maybe roughly center, and then draw an equator on this thing. Okay, and I can repeat the exact same process that I did down here. Like I just chose some numbers. So that's a strategy. I could just choose some numbers here, and let's say we're talking about volume, and the volume of a sphere is 4/3 pi r cubed. Okay, so we want to choose some really, really nice numbers that things are going to cancel out very nicely. And you might choose like 1 and 2, but look, I've got thirds down here. I've got thirds. So I want an even number. I want an even number for the bigger radius outside here, because I want to be able to divide it by 2 to get this inner radius. And I want my numbers to be divisible by 3. So a super convenient number for this outside radius would be 6. And then for the inside radius, taking half of that would be 3. Okay, so those are the two radii that we're going to use. And our strategy, again, once again, is volume of the inner one divided by the volume of this outer one. Whoa! Okay. So my probability that K is closer to the center I have 4/3, whoops, not a third, that's a third, 4/3 pi times my inner radius, which was 3, and then I'm going to cube. So don't go trying to cancel this out before this thing is cubed. Order of operations dictates that we have to cube before we can divide. All right, all of this divided by the volume of the whole entire cube, 4/3 pi times this times 6 cubed. Okay, so now let's simplify some stuff. Look, I don't even have to deal with the 4/3, it turns out, because as I arrange it in this fraction, I can see that all of this is going to cancel out with all of this. This is like 1. Okay, so let's get our cancellation crayon. There we go. And then all I have to do is 3 cubed. 3 cubed is 27. 3 times 3 is 9. And then 9 times 3 is 27. All right, and then 6 cubed. 6 times 6 is 36. And 36 times 6 would be another 36. Whoops. How about a 3 up there? And then 18 plus 3 more is 21. 216. All right. Does that reduce? Let's see. Let's put this thing in the calculator. Does 27 go into 216 divided by 27? It goes in exactly 8 times. Look at this. It reduces to an 1/8. So here's our probability then. Is that what you anticipated following this pattern? This was one-dimensional. This one was two-dimensional. And then finally a three-dimensional one. So think about this. This is 1/2 raised to the first power, 1/2 raised to the second power, and this is basically 1/2 raised to the third power. So the probability that an atom bouncing around inside of this sphere is going to land someplace closer to the center than it is to the outside of the sphere is exactly 1/8. Which brings us to the conclusion of this lesson, which was all about volume, being able to use various formulas, find the volume of prisms, pyramids, cylinders, cones, and spheres, and then we can maybe put that in an application in order to calculate probabilities with geometric solids.